Time is not absolute. It is flexible and relative, bending in response to gravity and velocity. This concept allows for phenomena such as time dilation, where a clock moving at high speeds or in a strong gravitational field ticks more slowly relative to a stationary observer. This mind-bending insight reshapes our understanding of aging, the movement of celestial bodies, and the potential for interstellar travel. Meanwhile, quantum mechanics offers an entirely different kind of strangeness. At the subatomic level, particles do not follow linear deterministic paths. They exist in a haze of probabilities, where multiple outcomes are simultaneously possible until measured or observed. The coexistence of these two realities forces us to confront a universe that behaves differently depending on the lens through which we examine it. Imagine the practical implications of these insights for humanity. If time can bend and particles can exist in multiple states at once, then the universe is far more malleable and dynamic than previously imagined. Technologies that were once considered science fiction, such as quantum computing, teleportation, and advanced energy manipulation, are now emerging from theory into experimental reality. Quantum computers exploit the principles of superposition and entanglement to perform calculations at speeds unimaginable with classical systems. These devices are not only revolutionizing computing but also challenging our understanding of information and its relationship to reality. Relativity, on the other hand, underpins the global positioning systems that guide planes and ships and informs the accuracy of satellite communications. The combination of these insights opens the door to a future where humans may harness the underlying structures of reality to navigate space, time, and information in unprecedented ways. The human mind itself is deeply influenced by these discoveries. When we confront the notion that particles can exist in multiple locations at once, that observation influences outcomes, and that space-time is not rigid, we begin to question our everyday assumptions about causality and the nature of consciousness. Could consciousness itself play a role in shaping reality at the quantum level? Experiments in the field of quantum biology suggest that even fundamental processes in living organisms, such as photosynthesis and avian navigation, may exploit quantum effects. If so, then the implications extend to human perception, decision-making, and creativity, suggesting a profound link between mind and the universe that Einstein never fully anticipated. The universe is not merely a passive stage upon which life unfolds, it is an active and dynamic field that may be responsive to our intentions in ways that science is only beginning to comprehend. One of the most compelling aspects of the Einstein quantum clash is the concept of entanglement, sometimes described as spooky action at a distance. Two particles that become entangled share a connection so profound that a change in the state of one instantly affects the state of the other, regardless of the distance separating them. This phenomenon challenges classical notions of locality and causation and suggests a universe in which everything is deeply interconnected at a fundamental level. The philosophical implications are staggering. If the cosmos is entangled, then separateness may be an illusion, and consciousness may not be as isolated as it seems. The study of entanglement is not merely a theoretical exercise, it has practical applications in the development of quantum communication systems that could transmit information with unprecedented security and speed. The potential to harness these properties of reality for human benefit is immense, yet requires careful consideration and profound ethical reflection. The pursuit of unification between relativity and quantum mechanics is one of the most ambitious and ongoing quests in science. The concept of a theory of everything seeks to reconcile the deterministic rules of space-time with the probabilistic laws of the quantum realm, providing a coherent and unified description of all forces and particles. String theory proposes that the fundamental constituents of the universe are not point particles but one-dimensional vibrating strings, whose modes of vibration correspond to different particles and forces. These strings exist in multiple dimensions beyond the familiar 3 of space and 1 of time, suggesting a universe far more intricate than human senses can directly perceive. Loop quantum gravity approaches the problem differently, positing that space itself is quantized into discrete units forming a granular structure of space-time. Both approaches remain incomplete and speculative, yet they highlight the creativity and rigor with which humanity seeks to understand the ultimate nature of reality. The mysteries do not end with theoretical constructs, they extend into observable phenomena that defy classical intuition. Quantum tunneling allows particles to pass through barriers that should be insurmountable according to classical physics, a principle that underlies technologies such as the scanning tunneling microscope and the development of new types of semiconductors. Relativistic effects are observed in the behavior of particles traveling near the speed of light in particle accelerators, confirming Einstein's predictions with extraordinary precision. The fact that these phenomena operate flawlessly despite our inability to fully intuit them underscores the importance of mathematics and experiment as tools for navigating a universe that is simultaneously comprehensible and mysterious. Each discovery reveals not only new capabilities but also new questions, reinforcing the notion that science is a journey rather than a destination. As we extend these concepts into the future, the potential applications of combining quantum mechanics with relativity are staggering. Consider the possibility of quantum navigation systems that account for relativistic time dilation, allowing spacecraft to traverse vast distances without error. Or quantum sensors capable of detecting minute changes in gravitational fields, offering unprecedented insight into the structure of the cosmos. In medicine, quantum imaging techniques could revolutionize diagnostics, while quantum simulations may accelerate drug development by modeling molecular interactions with extreme precision. The integration of these principles into technology promises to transform every aspect of human life, from transportation and communication to energy generation and healthcare, providing solutions to challenges that were previously thought insurmountable. Even at a philosophical level, the clash between Einstein and quantum mechanics reshapes our understanding of free will, determinism, and the nature of reality itself. In a deterministic space-time universe, every event is the inevitable consequence of prior states. Yet quantum mechanics introduces fundamental uncertainty at the core of existence, suggesting that outcomes may be influenced by probabilities rather than fixed laws. This duality invites deep reflection on the meaning of choice and agency in a universe that is simultaneously predictable and unpredictable. It challenges us to embrace ambiguity and cultivate a mindset of curiosity, wonder, and humility, acknowledging that our understanding of the cosmos is always provisional, subject to revision as new discoveries emerge. The interplay between certainty and uncertainty becomes not a source of anxiety, but a profound invitation to engage creatively and responsibly with the unfolding reality around us. Education and public engagement play a critical role in translating these complex ideas into broader understanding. By exploring the paradoxes of relativity and quantum mechanics through compelling narratives, thought experiments, and accessible examples, we allow more people to appreciate the strangeness and beauty of the universe. This engagement fosters critical thinking, creativity, and an appreciation for scientific inquiry, while inspiring future generations to pursue careers in physics, mathematics, and related fields. As the frontiers of knowledge expand, the opportunity to cultivate a scientifically literate society capable of navigating a rapidly evolving technological landscape becomes essential. Understanding the interplay of relativistic and quantum phenomena is not merely an academic exercise. It equips humanity with the tools to adapt, innovate, and thrive in a reality that is constantly revealing new layers of complexity. As we continue to explore these ideas, it is important to